Hello, and welcome to the tutorial on interest rate sensitivity, part 1. Let's start by reviewing the basics of bond price and yield to maturity. You may recall that yield to maturity is the average discount rate that would apply to all of a bond's cash flows such that they would sum up to equal the bond's market price. That's shown in this formula below. And for a bullet bond with an annual coupon rate C and a price P, each cash flow maturity would equal C, and then the final cash flow would equal 1 plus C. And so the price formula would become what's shown at the bottom. Now recall also that the bond price implies the yield to maturity and vice versa. So for example, suppose a 10-year bullet bond with an annual coupon of 10.5% is priced at 125. What is the bond's yield to maturity in this case? Well, this is very easy to do on our calculator. So let's do that. We input 10 into the N register, the price in PV, 125, and the payment and the future value will be opposite signs of the price. So we'll enter those as minus 10.5 and minus 100. So that means minus 10.5 is being paid every year through year 10, and then in the final year, minus 100 is being paid. So this corresponds to the cash flows of the bond. And then to obtain the yield to maturity, we just hit the IY key, and we get 6.9490. Okay, and remember that's in percent. So we can run this in reverse. So if we were to input 6.949 in the IY key and then hit PV, we would get 124.9996. Now, we didn't get 125. Why is that? Well, we have a little issue with rounding. If we re-input 6.949, we're inputting exactly that number. And if we look at more precision on what comes out of this register when we did it the first time, we'd see it wasn't really 6.949, but it was this thing below, 6.9489, and then lots of numbers. Okay, so this is something we're going to need to be careful about when we do these types of sensitivity calculations. So sometimes it will matter and sometimes it won't. All right, so how do we measure the bond's interest rate sensitivity? A common way is to measure the sensitivity to measure the sensitivity to a small change in its yield to maturity. So for example, we got the initial price here, P0, say that's the current price, and that implies a yield to maturity or vice versa. So we might input the price, get the yield to maturity. Then we input a slightly different yield, Y1, and we get a different price. And so the change in yield is delta Y, and the change in price is delta P, just being the difference between Y1 minus Y0 and P1 minus P0. And if we were to look at that in return terms, the return would be the change in price over the initial price. Okay, now bond price changes inversely with yield. So that means if we reduce the yield to maturity, so if we go from 6.949 to 5.949, or increase it and go to 7.949, we'll get different prices. And when the yield goes down, the price goes up, and vice versa. And you'll notice here that they changed in opposite ways by about the same amount, but not exactly the same amount. So if we were to look at this in a graph, it would look like almost a line. We're showing the price change here on the y-axis, and then this is the minus 1% yield and the plus 1% yield. And we would get both of these numbers just using our calculator. So we'd input 5.949, we'd get this number here, and then if we input 7.949, we'd get this number here. Okay. Now, to see the curvature effect that we saw a little bit of in the previous slide, let's increase the YTM range. So if we go, instead of plus or minus 1%, we do plus or minus 3%. We'll get different numbers. So we're going from 6.949 to 3.949 in the reduced YTM case. And we input that into our calculator and we get this, 153 and change. And then if we go in the other direction, we get 103. Now we're seeing a much bigger difference in the price change. And then we look over here, the graph is quite visible. So the solid blue line is the actual price that we would get by inputting various changes in yield to maturity. And then the dashed line represents kind of the linear approximation of that. And so we see for plus or minus 100, it's pretty close. Plus or minus like 0.5%, 50 basis points, is very close. But you get out to 3%, plus or minus, it's noticeably different. And that curvature is called convexity. Now, there are two common statistics used to measure this linear component of sensitivity to changing interest rates. And the first one is called the price value of a basis point. And that stands for the price gain or loss from a 1 basis point and change in yield to maturity. And you should know that a basis point, if you didn't already know, is 0.01%. So for example, if we know that the PVBP is 0.08, that means that a 1 basis point drop in the yield to maturity would result in a 0.08 point rise in price. So if the price were 110, it would go to 110.08. Now, the second common measure of linear price sensitivity is called modified duration. And this is defined as the ratio of the return gain or loss. So not the price gain or loss, the return gain or loss from a small shift in YTM to the size of that shift. So it's the ratio of these two. So for example, if the modified duration is 7, that means that a 1 basis point drop in yield to maturity results in a 7 basis point rise in price. And that would mean the 110 price would go to 110.077, not 07, 077. And that's because we're doing it in return terms. So the 110 would be multiplied by 1 plus this 7 basis points, and that would get us this 110.077. Now, if you're not familiar with the term duration, it may seem odd applied in this case. And I'll just note here that it comes from a mathematically related statistic known as Macaulay duration that we'll discuss in a later tutorial. This was developed in the 1930s as an alternative measure of maturity that included all the bond's cash flows. So the modified duration is a modified version of that, and this is really the one that's more commonly used today. So let's explore each of these in turn. So starting with the first sensitivity measure, PVBP, how does this work? So, or how do we calculate it? So let's do a YTM change, but an even smaller one that we were looking at before. So plus or minus 1 basis point. So our 6949 is going to change to 6939. And this is where the precision starts to matter. So we don't want to be re-inputting numbers willy-nilly here. So the price from the 6949, if we input that, would not have been 125, it would have been 124.996. Again, that's rounded to 4 decimal places, it keeps going. So if we were to then use that and go minus 1 basis point or up 1 basis point, we'd get these prices. And here you see, since it's a really small change in yield, the difference in magnitude between the up case and the down case is very small. They're almost the same. So if we're asking what is the price value of a basis point, well, it's about 0.082 and maybe 0.0821 if we were looking at the down case, or maybe 0.0819 if we were looking at the up case, or we could just average them because we don't want to have a bias one way or the other, and we would get 0.0820. And that's typically what would be done. Now, another efficient way to estimate it, and one I actually prefer, is rather than doing the up and down and averaging it, you can do a very small change and then multiply it. So let's start by computing the yield to maturity. So we, input everything but the yield. The maturity's 10, 125. We'll put 125 in here instead of the 124,9996. So we'll put in the actual price, the payment, and the future value as negative values, and we'll calculate this yield. And then we'll subtract 1/100th of a basis point from that. And then that means we'll have to multiply the final result by 100 to recover from that. So specifically, this is what we would do. So we would have calculated this, and then we would reclaim that. And we reclaim that because we don't want to lose the precision. We subtract 1 basis point, which means subtracting 0.0001, right? So it's going to be in this decimal place here, and that would give us 6.9489. That's what's going to show if our calculator is displaying to 4 decimal places. Then we would compute to PV. You might hit, depending on your calculator, you hit compute key and then PV, or more commonly, you just hit PV. And we get 125.000008. And we subtract 125 from that because we want to look at the change, right? We're seeing how much did it increase from that small drop in yield. And then we're going to multiply it by 100 because the change was only 1/100th of a basis point. And so that gets us up to the same 0.0820. Now, let's just be very aware here of the precision issue. So we're reclaiming this here because we don't want to lose these decimal places that we don't see. And so then when we subtract 1 basis point from it, it'll display this way, but we will have retained all of those extra digits. And then when we calculate the answer, we're getting something that we can rely on because we're looking at the actual 1/100th of a basis point difference here. And that's why we're able to get the accurate number. So just caution, if you do this method, be very careful not to re-input numbers and lose precision. Okay, so let's do a practice problem. So why don't you hit the pause and try this on your own. So we've got a 10-year bullet bond with an annual coupon of 4%, priced at 78. And so using the method, if you remember it, try to calculate the PVBP. Okay, so what you would have done is put in the new values because we got a new bond. So the maturity is still 10. The price now is 78, so that goes in the PV register. Future value is still going to be minus 100, but the coupon is 4%, so that's why we put the -4 there. And we would have gotten this 7.1547. Again, that's rounded to 4 decimal places. So we subtract our 1/100th of a basis point, and you'll see we get the difference right here. And then we hit the PV, and we get that number there, 70006 is what shows up. And then we subtract 78 and multiply by 100, and then we're going to get this additional precision. Okay, so you can see what's going on really by looking at beyond what's displayed. So these are the extra digits not displayed here. So we're not losing anything when we subtract the 1/100th basis point. And then even though this is displaying as a 6, this is actually what is coming out of there. And then when we multiply that by 100, we see it 0.0596. That's the PVBP. Now, you can also do this quite easily in Excel. So this is how that would work. I would just remind you of 2 functions that you're going to use. The rate function, which is doing essentially what the IY key was doing on your calculator. And that takes as inputs the maturity, the coupon, the price, and the face. And you got to be very careful here about a sign. So you'd put negative in front of coupon and negative in face and positive for price. Or you could do the reverse. That would work as well. And then the PV function works really like the PV on the calculator. So that would have the input of the YTM, the maturity, and then again, coupon and face, but being cognizant of the sign. And so if we had an Excel sheet that was set up like this with these as our inputs, 10, 10 and a half, and 125, 10, 4, and 78, those are the same two bonds we looked at with our calculator. We calculate the yield to maturity using this. Now I would note here that in Excel, different from your calculator, it will be in actual percent. So this is displayed as 6.95%, but it's actually being retained as 0.0695 and 0.0715, of course, followed by the extra digits. And then when we do our PVBP, what we're doing is we're taking that YTM, we're subtracting 1 basis point divided by 100, and then calculating the price for that new yield, subtracting price and multiplying the result by 100. So if we do that, embed that in this formula, we'll get exactly the same numbers that we got before. So you can either try that now in Excel. If not, I would encourage you to try it after the tutorial's over, just to make sure you can do this. Okay, so let's do an application. Why are we doing this? Why do we calculate PVBP? Well, it actually is a very, very powerful statistic, and we can use it as sort of the simplest application would be to estimate bond changes from modest yield to maturity changes. So you can think of it as when you're sort of positing what would happen if interest rates generally moved up or down by some modest amount, maybe not 1 basis point, but not a large amount, so that the linear approximation would be reasonable. So for example, if we wanted to say what happens if yield to maturity goes up by 25 basis points, well, we could calculate that precisely just by adding 25 basis points to our yield. So we had 695, that would become 720, and we would of course have to adjust basis points to percent by dividing by 10,000. That's the equivalent of multiplying by 0.01%. So if you get weird numbers here, you're messing up on this part here most likely. And then you just use the PV function in Excel to get the new price, and so you would get these numbers. So it would go from 125 to 122.97 and 78 to 76.53. So this is not using the PVBP. This is just calculating the new price directly. Alternatively, we could estimate it by just saying, well, we know the PVBP. So for example, in the first bond is 0.0820, and we know that we're changing 25 basis points. So the new price is approximately going to equal the old price minus that change, minus the 25 basis points, times the 0.0820, and that would give you 122.95. And it's very close to this, which is what you would expect because it's a small change. And so the difference, the error here is the difference due to curvature or convexity. It's minus 0.02. So if you were just trying to get rough ideas of sensitivity to, what would happen to the price for these modest changes, the PVBP would be a very quick way to do it. And similarly, same calculation for the other bond, and you see it's also very close. And then, this graph, just to remind you, is how it works. So we're looking at 25, so we're looking at kind of this range here. So that is, you can't really see the difference between the actual bond price and the linear estimate. Now, if we were to do changes out here, you probably wouldn't want to use PVBP in that case unless you were just really worried about a very gross estimate. Okay. So let's move on now to the second sensitivity measure. Remember that was modified duration, and here we're looking at return. So this reminds you of the definition. So it's a measure of the bond's return in percent from a small fall or rise in yield to maturity divided by the change in yield to maturity. And so what we would do is we would do a small delta YTM, a tweak of the YTM, and then we would get the change in price, divide that change in price divided by price, so that becomes the return associated with that small yield to maturity change, and then divide that by the yield to maturity. And then we add a minus sign. It could go here or it could go up here, it doesn't matter. And that just means modified duration will be positive, even though the slope is negative. The relationship is inverse. That's just a matter of convention. And so to be consistent with convention, you would put the minus sign there. Now, if you've already calculated the PVBP, this becomes even easier because you could use that as an intermediate step. You could say, all right, we know the delta price for 1 basis point change is what's the PVBP, divide that by the price, and then the yield to maturity change in that case would be minus 1 basis point, so that becomes the plus 0.01% here. So you could divide it by 0.01%, or alternatively, you could multiply this whole thing by 10 thousandths, because dividing by 0.01% is the same as multiplying by 10,000. Okay, so let's see how that works in practice. So let's go back to our 10-year 4% bond priced at 78. The maturity is 10, price is 78. These are our cash flows. We're going to calculate the yield. And then to get the modified duration, we're actually, the first 4 steps are exactly what you did to get the PVBP. So just repeat that and you get the PVBP. And then the only thing you do extra is you divide by the price and divide by 0.0001 or multiply by 10,000. And then that will get you the modified duration for this bond. So it had a PVBP of 0.0596. The modified duration then is 7.641. Okay, and then this can also be done easily in Excel, particularly if you've already gotten the PVBP, and that would be a reasonable way to do it, is calculate the PVBP, and then you don't need this intermediate step, but just to show you what happens if you divide PVBP by price, this would be, you get a tiny return here, and that's just your PVBP divided by your price. And then, or you could go the full step and say PVBP divided by price divided by 0.01%, and you would get the numbers that we got using our calculator. So we calculated 764 for bond 2. If we did the same calculation for bond 1, we get 656. Now, step back from the calculations and let's look at the numbers for a second. And there's something kind of curious here. So if you think of these as risk measures, and PVBP is showing 0.082 and 0.0596. So bond 1 has a higher PVBP, but it has a lower modified duration. So if you ask which bond is riskier, well, what's the answer? PVBP kind of suggests bond 1 is riskier. You get a bigger price change. And modified duration suggests the opposite. Well, what's happening is, remember, modified duration is in return terms. So the price of bond 1 is higher. So yeah, you're getting a bigger change for a 1 basis point move in bond 1 than bond 2. But as a percent of the value of the bond, actually bond 2 moves more. So you see the return, the gain or loss from that 1 basis point move is higher for bond 2. So if you were asking the question, well, if I were to buy $100 face of bond 1 versus $100 face of bond 2, then yes, this has a bigger a bigger volatility. But you would have made a much bigger investment in bond 1 because you would have had to pay $125 for that 100 face, whereas here you would have only paid $78. So if you were to ask differently and say, well, if I were to invest $100 in market value in the 2 bonds, then this is where modified duration would reveal that that was the riskier investment. So just to make a quick application using modified duration, it's really the same application we did for PVBP, but we're doing everything in return terms. So we start with our YTM that we calculated. We calculate the modified duration for the 2 bonds. And we could then say, well, what happens if there's a 25 basis point increase? Well, we get the new yield. We could recalculate the price. Okay, so this is not using modified duration. This is just recalculating it exactly. And these are the same numbers we got before. And then if we were to look at that in return terms, we say, all right, well, we lost 1.62% from a 25 basis point increase, right? It's inverse, or minus 1.892% for the second bond. Alternatively, we could use modified duration to get the that estimated return quite quickly. So it's just the minus YTM change. So the change is 25 basis points times the PVBP. And this is a mistake. That should be times the modified duration. Okay, so I have to fix that. So the estimated return then would just be the difference between the two. The mistake here is just in the notation. The actual numbers here are correct. And then if we're looking at in return terms, or look at the graph in return terms, we would see this. So just like we saw with PVBP, the sensitivity is very close for small changes, up to about 100 basis points, and then you see the curvature. So this is the same graph, but in return terms. Now we can compare these, and this really shows how the two relate to one another and why one sort of is more volatile and one in terms of price and the other in terms of return. So the blue line here represents the first bond, the 10.5% coupon, and the second bond, the orange is the 4%, the second bond. And so we see if we're looking at that in price change terms, the orange is going to get a smaller price change than the blue. But then if we look at it in return, it's the opposite. So the 4% bond is more sensitive in returns than the 10.5% bond. And that's reflected again, just these are the PVBP, same numbers summarized in the table. So that's about it. Let's just summarize our conclusions for part one. Bond price is inversely related to yield to maturity. We saw that, and we saw that for small changes, it's almost linear, but for large changes, the relationship is curved. We call that convexity. PVBP stands for price value of a basis point, and that measures the linear bond sensitivity to a YTM change in price terms. And then we saw modified duration. Modified duration is a very similar concept, but it's measuring the linear bond sensitivity to yield to maturity in return terms. Finally, just to remind you, when working on a financial calculator, be very attentive to retaining precision for intermediate figures. That won't be a problem for Excel, because Excel will automatically change it because you'll be not re-inputting, you'll just be pointing to cells. But for your calculator, you need to be careful. So that's it for the part one of the interest rate sensitivity tutorial. Thank you for listening.